Chapter 6, Queuing Models, Part 3, the last part of Section 1. So here we have the Little's law. So let's see what it does mean and how it's interpreted. So in this example, we have 5 customers in total in coming to our system in 20, let's say, time units, or let's say minutes. Okay, so yeah, we have in total 5 customers during 20 minutes. So if it divide n by t, the total time, it will be somehow the arrival rate, right? An estimation for arrival rate. So if it divide n by 20, we have 0.25. So this means every minute we have 0.25 arrival to our customer. So this means that almost every 4 minutes we have one customer. This is in average. One customer every 4 minutes, or 0.25 customers every 1 minute. Okay, so that's an estimation for the arrival rate. Okay, so for L hat and W hat, let's see how we calculate this. For L hat, here we need to actually multiply the number of customers in the system by their time length that number of customers are in the system, and then add up the numbers and then divide by the total time, which is 20, right? So for L hat here, we have here, as you see here, we have one customer in the system. Sorry, one customer in the system for 2 minutes here. Again, one customer for another 2 minutes, one customer for 4 minutes, and again one customer for 4 minutes, right? So we have one customer in the system for 2 plus 2 plus 4 plus 4 minutes, right? And we have 2 customers in the system for as you see here, 2 minutes here, and again 2 minutes here, right? So that will be 2 customers for 2 plus 2 minutes, and we have 3 customers in the system for just 1 minute, right? So yeah, it will be 3 times 1 divided by 20. So this will be 1.15, the number that we have right here. Okay, and for W hat, I mean the average total time spent by a customer in the system. So we do calculate this here as well. So for W hat, so if we take a look at the graph here, this means that here we have customer number 1 arrives system at time 0 and then departs at time 2, right? So customer number 1 is in the system for 2 minutes. Okay, then customer number 2 arrives the system at time 3 and then departs at time 8, right? So it will be 5 minutes. Customer number 2 is in the system for 5 minutes. Customer number 3 arrives system at time 7, as you see here, and then yeah, at time 7, and then departs the system at time 10, right? So this customer is in the system for oh, sorry, I made a mistake. The customer number 3 arrives the system at time 5 and departs the system at time 10. So again, it's in the system for 5 minutes. And customer number 4 arrives the system at time 7, and as you see here, departs the system at time 14. So again, for 7 minutes in the system. And customer number 5 arrives the system at time 16 and departs the system at time 20, right? So if we divide this by 5, the total number of customers, we'll have 4.6, the number that we have here. Okay, so I see here the L hat is 0.25. Sorry, lambda hat is 0.25, L hat is 1.15, and W hat is 4.6. So we see that there is a relationship between L hat, W hat, and lambda hat. Okay, so that's, and this in general it's called the Little's law. Okay, so the Little's law is this: L, the average number of customers in the system in the long term, equals lambda, the arrival rate, times W, the average time spent by a customer in the system in long term. Okay, so this is called Little's law. So this law tells us that we need to estimate just one of the two performance measures, L or W, because lambda is the input parameter. So we assume that we have it. We have already estimated that for our queuing model, but the L and the W are somehow the performance measures, right? So if we estimate just one of these two by a queuing model, by simulation, okay, and the other one can be calculated by the Little's law, okay? So yeah, and the good thing for this law, for Little's law, is this. This relationship actually holds for almost all queuing systems, regardless of the number of servers, the queue discipline, or any other special circumstances. So it's general and it holds for all queuing models. Okay. Here we have an informal proof for the Little's law. So here the ith rectangle has height 1 and length wi. So yeah, here is this is uh, the first rectangle for customer number 1. So as you see, the height is 1 and the length is 2, right? And this is the second rectangle for customer number 2. Again, the height is 2 and the length is W2. And this is the third rectangle for customer number 3. So if we consider this rectangle beside this one, so we'll have the height 1 with the width of 5, right? From 5 to 10, okay? And for customer number 4, again, we have these rectangles. If we put these 3 rectangles beside each other, then we'll have a rectangle with height 1 and the length of 7, right? And that's the last one. This is the rectangle for customer number 5 with height 1 and length of 4. Okay, so as you see here, by having this, the sum over I of Wi equals the area under LT, right? Integral from 0 to t of LT dt. Okay, so we have this equality here. And on the other side, we have lambda hat as n over t. Okay, so we know that L hat equals this area under LT divided by T, right? So if we multiply this by n over n, so n over n is 1, right? And if you multiply anything by 1, it won't change, right? So n over n, so here we can actually have this. So by having n over n, we can say we have n over t times 1 over n, and we know that the integral from 0 to t lt dt equals to sum over I of wi, right? So by having this, as you see here, we have this. So n over t is the lambda hat, and this is the L hat, and this is the W hat, right? So as you see here we have L hat equals lambda hat times W hat, right? So yeah, this is an informal proof for the Little's law, okay? So what's the server utilization? If we assume that we have just one server, so if we have single server, so row hat an estimation for server utilization will be this: total busy time for the server divided by T. Okay, so this means like this. Or we can say T minus T0 the times that we have no one in the system, so the server is idle. So T minus T1, T0 will be the busy time for the server. Again, if we divide this by T, that will be the server utilization rate. Okay, so for this example, it's 0.85. So because as you see here, we have 1 minute here and another 2 minutes here. So in total, we have 30 minutes that there is no customer in the system, so the server is idle, but the rest of the times the server is busy. So 20 minus 3 divided by 20 will be 0.85, the server utilization rate for this example. Okay. For the single server model, assume that the average arrival rate is lambda. So here we assume that we have in average lambda customers arriving system per time unit. And let's say the average service rate is mu, right? So if we divide mu by 1, I mean 1 over mu, that will be the average service time. So keep in mind that we have two terms here, rate and average time. So if we have the rate, so if we divide 1 by that rate, that will be the average time between two successive arrivals or services. Okay, so for example, here let's say we have a system and the time unit is 1 hour. So let's say the time unit is 1 hour, and let's say lambda is 5. So what does it mean? This means that it says that we have in average 5 customers arriving in the system per hour. So the inter arrival time here will be 1 over 5, right? Or 0.2, right? 0.2 hours, 0.2 hours, or in minutes it will be 12 minutes, right? So this means every 0.2 hour or every 12 minutes we have one customer arriving to our system. Okay, and the service time here, let's say the mu is 8. So this means that the server can serve 8 customers per hour. So again here 1 over mu, or the average service time ES equals 1 over mu, and it will be 0.15, right? So here the row, so here we have 5 customers arriving in the system, and each customer takes 0.15, 0.15 hours. So if we multiply the total number of customers, 5 per hour, by the time that each customer takes to serve. So in general, we will say that we have 0.75 hours per hour that server is busy serving those 5 customers, right? So since it's for time unit, so we'll say it's a rate actually, right? It's 75% actually. So this means that in 75% of times the server is busy to serve the customers. Okay, so as you see here, if you multiply the arrival rate by the average service time of each customer, which means lambda over mu, that will be the server utilization rate. So here we have rho, so lambda is 5 and mu is 8. So 5 over 8, or 5 times 0.15 will be 0.75 the server utilization rate. Okay. So for server utilization rate, we saw that it can be calculated by this T minus T0 over T, or for a single server model in long run, it's this lambda over mu. I mean the arrival rate divided by the service rate. Okay, so in order to be, in order to have a stable service system, we need to have this condition: lambda should be less than mu, or rho should be less than 1. So this is necessary in order to have a stable system, because if lambda be greater than mu, this means that the length of the waiting line will approach to infinity in long term, and so that system is not stable, right? And if we have more than one server in the system, let's say we have C servers in the system, then rho will be this lambda divided by C mu. I mean, so yeah, we have C servers. The service rate for each server is mu. So if you multiply C by mu, that will be the total service rate, right? So yeah, the arrival rate divided by the total service rate will be the utilization rate, right? So yeah, the number of busy servers LS will be rho times C, or lambda over mu. And again, for this multiple servers, we need to have lambda should be less than C mu. So this condition is necessary in order to have the system as a stable system. Okay. In multiple server queuing models, we have the utilization rate as this, right? Lambda over C mu. So if we increase the number of servers, then we have more servers, then the utilization rate rho will be low, right? So yeah, see here, if we increase the number of servers, then lambda over C mu will be decreased. So this means we will have a lower utilization rate, right? So in this case, by having more servers, we have lower utilization rate, but on the other side, we have a shorter waiting time, shorter waiting line, right? But and if we decrease the number of servers, then rho will be higher, rho will be higher, but the queue length and waiting time can be long. So as you see here, we need somehow an optimization here. So what will be the optimal number of servers, right? That's the question, and we can obtain the optimal number of servers if we have the parameters like the cost of server, the cost of waiting time for customers, and so on. So by having those parameters, we can build an optimization model here in order to optimize the number of servers in the system. Okay, so this is was the part 3 of section 1. So we are done on section 1 for this week. So next week we will have the queuing models in a steady state situation. Okay, thank you.